Tonight, we're going to confront one of the strangest facts in all of physics. Every electron inside your body carries something physicists call spin. It behaves like angular momentum, the very same quantity that keeps a spinning top upright and lets a figure skater whirl faster by pulling in her arms. This spin is real. It can be measured with extraordinary precision. It can be handed from one particle to another. It even helps the magnets on your refrigerator cling to the door. And yet, when physicists look closer, they discover something bizarre. Nothing is actually turning. An electron is not a tiny ball rotating on an axis. If it were, its surface would have to move faster than light just to match what we measure. So what is spinning when nothing spins? What is this hidden angular momentum sealed inside every particle that builds you? Before we go any further, if you find these deep dives into the hidden machinery of reality worthwhile, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Hold up your hand and look at it. Every atom in that hand is built around a nucleus, and around that nucleus move electrons, and every single one of those electrons is doing something right now that no one has ever fully been able to picture. Each one carries a fixed, unchangeable amount of angular momentum. Angular momentum is the physicist's word for the quantity of turning that something has, the same quantity locked inside a spinning top, a rotating planet, or a figure skater pulling her arms in to whirl faster. The electron has this turning quantity built into it, permanently, and it can never be sped up or slowed down. You cannot make an electron spin faster. You cannot make it stop. It arrives into existence with exactly this much until the day it is destroyed. That should already feel strange, because in the ordinary world, angular momentum is something an object has because it is physically rotating. A wheel has angular momentum because its rim is moving around its hub. A planet has angular momentum because its surface is sweeping around its axis. So the obvious guess, the guess almost everyone makes, and the guess that many brilliant physicists made a century ago, is that the electron must be a tiny ball turning on some internal axis. That is where the name comes from. That is why we call it spin. And here is the contradiction we're going to spend our time together untangling, because it is one of the most beautiful contradictions in all of science. The electron genuinely behaves like it is spinning in every way we can measure, but it is almost certainly not a little sphere rotating in space. When you look closely at the numbers, the spinning ball picture doesn't just get a little wrong, it shatters completely. So let us start with what angular momentum actually is in the world you already know, because everything that follows only makes sense if we're careful here. Imagine a child on a merry-go-round sitting near the outer edge. As the platform turns, the child sweeps in a great circle. That child has angular momentum, and it depends on three things: how much mass is moving, how far that mass sits from the center, and how fast it is going around. Move the child closer to the center, and the angular momentum drops. Push the platform faster and it rises. This is real, physical, mechanical rotation. There is a center. There is something at a distance from that center, and that something is traveling around the center. This is the picture our brains evolved to understand, because we have watched wheels and thrown stones and spun in circles as children until we felt dizzy. Now, physicists actually split this idea of turning into two different kinds, and the difference between them is the hinge on which this entire story turns. The first kind is called orbital angular momentum, and it is exactly the merry-go-round. It is the angular momentum something has because it is moving through space, travelling around some point or some axis that sits outside itself. The Earth travelling around the Sun has orbital angular momentum. A ball on the end of a string swung in a circle has orbital angular momentum, and inside an atom, an electron occupying its cloud around the nucleus has a version of this too. The electron's quantum state can carry orbital angular momentum that describes, loosely, how its wave is wrapped around the central nucleus. This orbital kind is the intuitive kind. It is genuine motion of a thing round a separate point. But there is a second kind, and this is the strange one. This is intrinsic spin. Intrinsic means built in, belonging to the thing itself, not borrowed from any journey through space. An electron sitting perfectly still, not orbiting anything, not travelling anywhere, still carries this second kind of angular momentum. It is not going around any external point. There is no centre outside itself that it circles, and yet the angular momentum is unmistakably there. This is what makes spin so puzzling. Orbital angular momentum describes motion around something else. Intrinsic spin describes a property that the particle simply has, the way it has a certain mass or a certain electric charge. It is part of the particle's identity, woven into what the particle fundamentally is. When physicists in the early 1920s first ran into evidence for this built-in angular momentum, the temptation to picture a spinning sphere was overwhelming, and honestly, who could blame them? Two young researchers proposed that the electron was a small rotating charged ball, and that its rotation was the source of the extra angular momentum and the extra magnetism that experiments were revealing. It was a bold, physical, satisfying idea. You could draw it on a chalkboard. You could hold up your fist and turn it. And for a moment it looked like the mystery had a face. But the moment anyone tried to make the numbers behind that picture actually work, the whole thing fell apart in a way that was impossible to ignore. Here is the problem, and it is worth walking through slowly because it is the reason we cannot simply say the electron is a tiny top and be done with it. Experiments tell us how much angular momentum the electron carries. It is a very specific, very small amount. Now, if that angular momentum comes from a physical ball spinning on its axis, then the size of that ball matters enormously. Remember the merry-go-round. Angular momentum depends on how far the moving mass sits from the centre. The electron is astonishingly tiny. Every experiment we have ever done trying to measure its size has come up empty. As far as we can tell, the electron has no measurable size at all. It behaves like a point, smaller than anything we have ever been able to resolve, far smaller than the nucleus, far smaller than a proton. And here is the trap that springs shut. If you take that fixed amount of angular momentum and you try to produce it with a ball that is that impossibly small, then the surface of that ball has to be moving unbelievably fast, because it has almost no distance from the centre to work with. The smaller you make the sphere, the faster its surface has to whirl to keep the same angular momentum. And when you actually run the calculation, you find that the equator of this supposed electron ball would have to be moving not just fast, not just extremely fast, but many times faster than the speed of light. Exactly how many times depends on what size you generously assume for the electron, but every reasonable estimate lands far beyond the light barrier, and the speed of light is the universe's absolute limit. Nothing carrying mass and energy can reach it, let alone blow past it by any factor at all. The spinning ball model doesn't just strain against physics, it demands something the universe flatly forbids. You might try to rescue the picture. Perhaps you say the electron is not truly a point, Perhaps it is a little larger, large enough that its surface can turn at a sensible speed. But this rescue immediately collides with a wall of evidence. Every experiment we have, from the enormous energies inside particle accelerators to the exquisitely precise behavior of electrons in atoms, tells us the electron shows no sign of internal structure and no sign of a surface. If it had a size big enough to spin gently, we would have detected that size long ago in 1,000 different measurements. We have not. The electron stubbornly behaves like a point with no innards, no skin, no equator, nothing to rotate. And the spinning ball model has a second failure, one that is just as damning. A rotating charged sphere would produce magnetism, and you could calculate exactly how much. The electron does produce magnetism, and we can measure exactly how much. When you compare the two numbers, they do not match. The electron is about twice as magnetic as a simple spinning charged ball of its angular momentum has any right to be. There is a number physicists attach to this, and its value comes out close to 2 rather than close to 1. And that factor of roughly 2 is not something the classical spinning ball can explain at all. The particle is behaving as though it turns, but it produces twice the magnetism a real turning object of that angular momentum would. The mechanical model doesn't just fail to reach the finish line, it runs the wrong race entirely. So now we are standing at the heart of the contradiction, and it would be easy to draw the wrong conclusion. It would be easy to throw up your hands and say that the physicists simply chose a bad name, that they slapped the word spin onto something that has nothing to do with turning, and that the whole thing is a linguistic accident we're now stuck with. That conclusion is tempting, and it is wrong, and understanding why it is wrong is the key to everything. Because here is the thing. Spin behaves like angular momentum in every single way that actually counts. This is not a loose metaphor. It is not a poetic label. When physicists write down the mathematics that describes the electron's spin, that mathematics is precisely the mathematics of angular momentum. It obeys the same rules. It combines with other angular momenta according to the same arithmetic. And most importantly, it participates in the great conservation law that governs all turning in the universe. Angular momentum is conserved. In any closed system, the total amount of turning cannot simply appear or vanish. It can be moved around, handed from one object to another, but the books must always balance. And spin sits inside those books as a full and equal member. Think about what that means. If spin were just a made-up label with no real connection to rotation, you could ignore it, and the accounting of angular momentum in the universe would still work, but you cannot ignore it. If you leave spin out of the ledger, the books do not balance. There are real experiments where a beam of light, which carries its own kind of spin, strikes a small suspended object and physically makes it twist. The spin of the light is transferred and becomes the ordinary visible mechanical rotation of the object you can watch turning. The intrinsic spin of particles has been converted directly into the everyday spinning of a thing you could hold. If nothing were really turning, this would be impossible. You cannot pour angular momentum out of an empty cup. There is a famous demonstration of this idea involving magnetism. If you take an iron cylinder and you flip its magnetization, you are, at the deepest level, flipping the alignment of the spins of countless electrons inside it. And when you do that, the cylinder itself begins to physically rotate, ever so slightly, to compensate. The intrinsic spin of the electrons and the mechanical turning of the whole cylinder are the same currency. Change one, and the other must respond to keep the total conserved. This was measured over a century ago, and it is one of the clearest possible proofs that spin is not a bookkeeping fiction. It is real angular momentum that can be traded for the ordinary kind, so the word spin is not a mistake. The physicists who chose it were not being careless. They were pointing at something true. This quantity is angular momentum genuinely and measurably. What was mistaken was only the mechanical picture that first came bundled with the word, the image of a tiny globe rotating on a tiny axle. That image is the part that fails. The angular momentum is completely real. The rotating ball is the illusion. And separating those two things, keeping the reality while releasing the false picture, is the single most important move in understanding what spin is. Let me put the distinction as sharply as I can. When we say the electron is not really spinning, we do not mean that its angular momentum is fake. We mean that there is no little material object turning through space to produce it. The angular momentum does not come from mass sweeping around a center. It comes from somewhere far stranger and far more fundamental. It is a property of the electron's quantum state itself. And to feel the weight of that sentence, we have to say something about what a quantum state even is. A particle like an electron, in modern physics, is not a tiny marble sitting at a definite spot with a definite motion. It is described by a quantum state, a mathematical object that captures everything that can possibly be known about the particle, where it might be found, how it might be moving, and crucially how it is oriented in a sense we are about to explore. This state is not a picture of a solid thing. It is closer to a description of possibilities, of tendencies, of the ways the particle will respond when you interact with it. And spin is one facet of that state. It is not a motion the particle performs. It is a feature of how the particle's state is put together, and above all of how that state behaves when you rotate your point of view. That last idea is the doorway to everything that comes next, so let me plant it here, even though we will return to it in far more depth. In physics, angular momentum is deeply tied to rotation, but not necessarily the rotation of an object. It is tied to how things respond to rotation. If you take a system and turn it, and ask how its description changes under that turn, the answer is governed by its angular momentum. Orbital angular momentum tells you how a particle's position in space description changes when you rotate the whole arrangement, and intrinsic spin tells you how the particle's own internal state changes when you rotate it, even if the particle is sitting perfectly still at a single point. The electron does not need to be a sphere sweeping around an axis. It only needs to have an internal state that transforms in a particular way when space itself is rotated, and it does. That transformation behavior is the spin. It is angular momentum without a moving surface turning without a thing that turns. If that sounds almost paradoxical, hold on to the feeling, because it is exactly the feeling that makes this topic worth exploring. We are so used to angular momentum meaning a physical object going around that the idea of angular momentum belonging to a state rather than a motion feels like a contradiction in terms. But nature is under no obligation to match the intuitions we built from watching wheels and merry-go-rounds. At the scale of a single electron, the familiar rules that connect turning to a rotating body simply loosen their grip, while the deeper rules, the ones about conservation and about how states respond to rotation, hold as firmly as ever. Let me use the electron as our anchor, because it is the most familiar carrier of spin and the one whose behavior touches your life most directly. But I want to be careful not to leave you thinking spin is only an electron's quirk. Spin is carried by an enormous cast of particles. The particles of light carry spin. The building blocks inside protons and neutrons carry spin. The protons and neutrons themselves carry spin. even the elusive particles that stream through your body by the trillions every second carry it. Spin is not a special accessory bolted onto the electron. It is one of the basic properties a particle can have, as basic as mass and charge. The electron is simply our clearest window into it, so we will keep returning to the electron while remembering that what we learn reaches much further. Now, one more thing before we move forward, because it matters and it prevents a misunderstanding. When physicists measure the electron's spin, they find that its total amount is fixed. It is often labelled as spin 1/2, and we will spend real time later untangling what that fraction means, because it does not mean the electron is turning at half of some speed, and it does not mean the electron is halfway rotated. For now, simply hold this. The total spin of the electron is a fixed permanent number, the same for every electron in the universe, and it cannot be increased or decreased. This is utterly unlike the merry-go-round, where you can spin the platform faster or slower at will. You cannot negotiate with an electron spin. It is what it is, identically, for every electron that has ever existed or ever will. Contrast that with orbital angular momentum inside an atom, which can take various values depending on how the electron's wave is arranged around the nucleus. An electron can occupy states with more or less orbital angular momentum, but its intrinsic spin is untouched by any of that. Whether the electron is deep in an atom, or flying freely through a vacuum, or drifting through the cold emptiness between stars, its spin is the same fixed amount. This permanence is one of the strongest signs that spin is not a motion the electron happens to be performing at the moment, but a fixed attribute of what the electron is. A motion could be changed. This cannot. So step back and take in where we've arrived. We began with a handful of atoms, each atom built around electrons, each electron carrying a permanent measure of angular momentum. We watch the natural instinct to picture that angular momentum as a tiny spinning ball, and we watch that instinct collapse under two crushing failures: a surface that would have to move impossibly faster than light, and a magnetism that comes out roughly twice too strong. We resisted the lazy escape of declaring the name a mistake, because spin passes every real test of being angular momentum. It obeys the mathematics of angular momentum. It participates in the conservation of angular momentum. It can be physically traded for the visible turning of real objects, twisting suspended mirrors and rotating magnetized cylinders. And so, we were forced toward a stranger and truer conclusion. The angular momentum is real, but it does not come from a rotating body. It is a property of the particle's quantum state, tied to how that state transforms when space is rotated. That is the seed of the whole picture, and everything from here grows out of it. Because once you accept that spin lives in the quantum state rather than in a spinning object, a cascade of questions opens up, and each one has a precise and often astonishing answer. If nothing is turning, then what happens when we actually try to measure the direction of the electron's spin? Do we find an arrow pointing somewhere definite, the way a real spinning top points its axis at a definite place in the sky? Or do we find something that refuses to behave like an arrow at all? When we ask the electron which way its spin is pointing, does it even have an answer waiting? Or does the very act of asking help decide it? And how can a particle have a definite amount of spin in total, yet somehow not have a definite direction for that spin until we look? These are not idle riddles. They were answered decisively by one of the most elegant experiments in the history of physics, an experiment in which a simple beam of atoms was sent flying through a cleverly shaped magnetic field, and what came out the other side split the world of physics open. The beam did not smear, it did not spread. It split cleanly and sharply into separate spots, as though nature could only give two answers to a question we assumed should have infinitely many. And in that split lies the next great clue to what spin truly is, and to why. Even though the electron carries genuine angular momentum, nothing inside it is turning like a ball at all. Picture a narrow beam of atoms flying through empty space, aimed like a thrown dart at a distant screen. These atoms have been prepared carefully, heated in an oven until a few of them stream out through a tiny opening, then funneled into a thin ribbon of a beam. Each atom carries an electron whose spin gives the whole atom a small magnetic character, so that every atom behaves like an unimaginably tiny bar magnet drifting through the vacuum. Now we send this beam between the poles of a specially shaped magnet, a magnet built so that its field is stronger on one side than the other, uneven across the gap, and then we watch where the atoms land. What happens next is one of the cleanest, strangest, most decisive results in the history of physics, and it is the moment where the reality of spin stops being an abstract argument and becomes something you can practically see with your own eyes. Let me first tell you what should happen, according to the comfortable picture we spent the last stretch of time demolishing. Suppose the electron really were a tiny spinning ball, a little magnet whose axis could point in any direction at all. Some atoms would have their magnetic axis pointing straight up, some straight down, some sideways, some at every conceivable angle in between, because a randomly oriented collection of little magnets should point every which way. When such a magnet passes through an uneven field, it feels a push, and the strength and direction of that push depend on how the magnet is tilted. A magnet tilted fully one way gets shoved hard in one direction. A magnet tilted fully the other way gets shoved hard the opposite direction. A magnet lying flat feels almost no push. Everything in between feels something in between. So if the electron were a classical little magnet free to point anywhere, the beam should spread out into a continuous smear, a smooth vertical band on the screen, dense in the middle and fading toward the edges, capturing every possible angle of tilt. That is the prediction of the spinning ball world. A smear, a gradient, a continuous spread of outcomes. That is not what happens. What actually happens is that the beam splits. It divides into two separate, distinct spots, one shoved up and one shoved down, with a clean gap of nothing in the middle. The atoms do not smear across every possible position. They arrive at exactly two places, as though each atom, when asked which way its spin points along the up-down direction of the magnet, could give only one of two answers, fully up or fully down, nothing in between. No atom lands in the middle, no atom lands at a gentle tilt. The continuous rainbow of angles that the classical picture demanded simply does not appear. In its place stand two sharp marks, and that gap between them is one of the most important empty spaces in all of science. This is the experiment that carries the names of the two physicists who performed it, and we will call it the Stern-Gerlach experiment. It was carried out in the early 1920s, before anyone even had the full theory of quantum mechanics to explain it, which makes the result all the more astonishing. They were not looking to confirm a prediction about spin, because the modern idea of spin did not yet exist. They stumbled into a fact about nature that no one was prepared for. When you measure the spin of a particle along a chosen direction, you do not get a continuous range of possible values. You get a small fixed set of discrete outcomes. For the electron along any single direction, you get exactly two. This word, discrete, is the heart of it, so let me dwell on it. In the everyday world, when you measure the tilt of a spinning top, you can get any angle. The top's axis can point at the ceiling, or 15 degrees off, or 42 degrees off, or any value you like, smoothly and continuously. There is no gap in the possible answers, but the electron's spin refuses this smoothness. Along a given axis, its measured value is quantized, meaning it comes only in specific, separated steps, with forbidden gaps between them. This is the same word we use when we say energy in an atom comes in quantized levels, or that electric charge comes in quantized units. Nature at this scale does not always offer a continuous dial. Sometimes it offers only a switch with a fixed number of positions, and for the electron's spin along any direction, that switch has exactly 2 positions. Now, here is where we must be extraordinarily careful, because there is a seductive misreading of this experiment that feels reasonable and is completely wrong. You might think, well, perhaps each electron always did have a definite spin arrow pointing somewhere, and the magnet simply sorts them. Perhaps the electrons that happen to be pointing more or less upward get sent up, and the ones pointing more or less downward get sent down, and the experiment is just a sorting machine reading a label that was already there. In this reading, the spin arrow is a hidden but definite thing, like a compass needle sealed inside each atom, already pointing some real direction, before we ever switch the magnet on, and all we did was discover which atoms leaned which way. This reading is wrong, and the way we know it is wrong is one of the most beautiful chains of reasoning in physics. The clue is already hiding in the result. Remember, we did not get a smear. If each electron had a definite arrow pointing in some real pre-existing direction, and those directions were spread randomly across all angles, then even a sorting machine would produce a smear. Because the amount each atom gets pushed depends on how much its arrow tilts along the magnet's direction. An arrow tilted only slightly should get pushed only slightly. An arrow tilted fully should get pushed fully. So a collection of pre-existing arrows at every angle would still land at every position on the screen. The fact that only 2 positions appear tells us the electrons were not carrying pre-existing arrows at every angle that the magnet merely read off. Something deeper is going on. The measurement is not reading a hidden value. It is producing a definite value where there was none fully determined before. Let me make this even sharper, because the distinction between reading a value and producing one is the whole game. In the classical world, measurement reveals what was already true. You put a thermometer in water, and it reveals a temperature the water already had. The thermometer does not create the temperature, it reports it. Our deep instinct is that all measurement works this way, that the world has definite properties sitting there in the dark, and measuring simply turns on a light so we can see them. Quantum mechanics breaks this instinct. When you measure the electron's spin along the up-down direction, you're not turning on a light to see a value that was already sitting there fully formed. You're asking a question that forces the electron to commit to one of exactly 2 allowed answers, and until you ask, the electron may not have had a definite answer to that particular question at all. To feel why this must be true, we need to talk about what the electron's spin state can be before measurement, and here we meet the idea that quantum systems can exist in combinations of possibilities. An electron's spin, before we measure it along the up-down direction, might be in a state that is neither purely up nor purely down, but a genuine blend of both possibilities held together at once. This is not a statement about our ignorance. It is not that the electron is secretly up or secretly down, and we just do not know which. It is that the electron's state is truly a superposition, a real combination of up and down that has its own definite character, but a character that is not simply one or the other. When we then send that electron through the up-down magnet and force a measurement, the blend resolves into one of the two allowed outcomes, and it does so probabilistically, with the odds set by how the blend was weighted. So the two spots on the screen are not two piles of electrons that were always up or always down. They are two piles created by the act of measuring. And this is what people mean at the deepest level when they say the electron is not a tiny top with an axis pointing in a definite direction. A real top always has a definite axis. You never catch it in a blend of pointing up and pointing down at the same time. The electron's spin before measurement along a given axis can be exactly such a blend. The spinning top picture fails here just as thoroughly as it failed when we found the surface would have to outrun light. Now let me introduce a piece of vocabulary that people often stumble over and clear up a misunderstanding that has confused many. We say the electron is a spin 1/2 particle. That fraction, 1/2, is the label for the total amount of intrinsic spin the electron carries. But it is desperately important to understand that this 1/2 does not mean the electron is spinning at half of some speed, and it does not mean the electron is rotated halfway around, and it certainly does not mean the electron is only half participating in some rotation. The number 1/2 is not a speed, and it is not an angle. It is a label that classifies the kind of spin the electron has, drawn from the mathematics of angular momentum, which only permits certain values. Some particles are spin 0, some are spin 1/2, some are spin 1. These labels tell you what family of transformation behavior the particle belongs to, and in particular, they tell you how many outcomes you will get when you measure the spin along a direction. Here is the rule that ties the label to the experiment. A particle with total spin 1/2 gives exactly two possible outcomes when you measure its spin along any single chosen direction. Those two outcomes are often described as spin up and spin down along that direction, and their values come out as +1/2 and -1/2 in the natural units physicists use. That is why the beam split into two. The number of spots is fixed by the spin label. A spin 1/2 particle produces 2 spots. A different particle with a higher spin would produce more spots, 3 or 4 or more evenly spaced. The electron gives 2 because it is spin 1/2, and this connection between an abstract label and a concrete count of spots on a screen is one of the tightest and most beautiful correspondences in physics. And now I want to draw the crucial distinction that this vocabulary hides, because it will matter enormously as we go on. There is a difference between the total spin of a particle and the projection of that spin along a direction you choose to measure. The total spin, the 1/2, is a fixed property of the electron, unchangeable, the same for every electron everywhere. But the projection, the amount of spin that shows up along whatever axis your magnet happens to point, is the thing that comes out as one of 2 discrete values when you measure. The total is fixed and permanent. The projection is what the measurement extracts along a specific direction, and it can come out as up or down depending on the outcome. Confusing these two ideas, the total spin and the measured projection, is one of the most common sources of misunderstanding in this whole subject. The total is the character of the particle. The projection is the answer to a specific question you asked, by pointing your apparatus a specific way. So far we have pointed our magnet in one direction, the up-down direction, and found 2 outcomes. But now comes the twist that turns the Stern-Gerlach experiment from a curiosity into a revolution, and it is the part that finally destroys any lingering hope that spin is a hidden arrow waiting to be read. What happens if, after we measure the spin along the up-down direction, we then measure it again along a different direction, say left-right? Let us do it carefully. First, we send the beam through the up-down magnet and it splits into two. We block the lower spot entirely and keep only the atoms that came out spin up along the up-down direction. Now we have a clean, pure beam. Every atom in it has been measured and found to be spin up along up-down. If spin were a definite hidden arrow, these atoms now all point up cleanly, with no ambiguity. So now we take this pure up beam and send it through a second magnet, but this one is rotated 90 degrees, so it measures spin along the left-right direction instead. What should happen? If the atoms are all pointing straight up, then along the left-right direction they should have no lean either way. Their arrows point up, which is sideways to the left-right question, so a classical magnet would give them no push left or right, and they should all sail straight through undivided, landing in a single central spot. That is the classical expectation for a beam of upward-pointing arrows asked a sideways question. That is not what happens. Instead, the pure up beam splits again into two spots, left and right, in equal halves. Half the atoms that would definitely spin up along the vertical direction now come out spin left, and half come out spin right. The measurement along the new direction produces two outcomes all over again, even though we had already pinned down the spin along the old direction. The electrons did not carry a definite left-right answer waiting to be read. When we asked the vertical question, they gave a definite vertical answer, but that vertical answer did not fix the horizontal answer. When we then asked the horizontal question, they had to generate a fresh answer, and they did so probabilistically, splitting 50-50. And here is the final blow to the hidden arrow idea. Take those atoms that just came out spin left, a pure beam now definitely spin left along the horizontal direction. Send them back through the original vertical magnet. Surely you might think they are still spin up along the vertical, since we measured that earlier and only afterward measured horizontal. But no. The vertical beam splits again, into up and down, 50-50. The act of measuring the horizontal spin has erased the definiteness of the vertical spin. The electron cannot hold a definite value along both directions at once. Pin down one, and the other goes fuzzy, becomes an even blend of its two possibilities, ready to give a fresh random answer when asked. This is the profound heart of spin, and it is a genuine feature of the quantum world, not a limitation of our instruments. The different components of spin, the value along up-down, the value along left-right, the value along forward-back, cannot all have definite values at the same time. Knowing one with certainty means the others are genuinely undetermined. This is not because our magnets are clumsy. It is not because the measurement jostles a delicate arrow. It is because there is no arrow with three definite components sitting there to be measured. The electron's spin state simply does not contain simultaneous definite answers to the vertical and horizontal questions. It is a fundamental incompatibility built into the structure of the quantum world. Physicists have a precise name for this incompatibility. They say that these different spin components are non-commuting observables. The word commuting comes from the idea of order not mattering. When two operations commute, you can do them in either order and get the same result. When they do not commute, order matters. Measuring the vertical spin and then the horizontal spin does not give the same situation as measuring horizontal and then vertical, because each measurement disturbs the possibility of a definite answer to the other. The two questions interfere with each other. You cannot answer both at once with certainty. No matter how clever or gentle your apparatus. This non-commuting quality is one of the deepest signatures of quantum mechanics, and spin is its purest, simplest example, because it lives in a world of just two outcomes, rather than the endless continuum of positions and momenta. Let me pause to guard against another misunderstanding, because it is easy to slide into. When I say the second measurement produces a fresh answer, I do not mean the magnet is magically creating spin out of nothing. The apparatus is not injecting angular momentum into a blank particle. The electron already possessed its full, fixed total spin the entire time. What the measurement does is not create the spin, but force the particle to commit to a definite projection along the direction you chose to ask about. The spin was always there in total. What was not there beforehand was a definite answer to the specific, directional question you posed. The measurement reveals one of the allowed outcomes for that chosen direction. It does not conjure angular momentum from the void. The distinction is subtle but essential. The device selects an allowed answer. It does not fabricate the underlying property. And this is exactly why changing the direction of your magnet changes everything. When you rotate the magnet from vertical to horizontal, you are not measuring a different amount of the same thing. You're asking a genuinely different question. Spin along the vertical direction and spin along the horizontal direction are different, incompatible aspects of the electron's state. By choosing which way to point your apparatus, you choose which question to ask, and the electron can only give you a definite answer to that one question, at the cost of leaving the other questions unanswered and blurred. There is no way to point your magnet so cleverly that it reads all directions at once. The universe does not permit it. You get to ask one directional question, and you get one of a fixed set of discrete answers, and in the asking you scramble the answers to the perpendicular questions. Sit with how radically this departs from the world of spinning tops. A real top has a definite axis pointing in a definite direction in space, and that single axis simultaneously determines its lean along the vertical, the horizontal, and every other direction at once. All consistent, all readable, all real. The top's orientation is a single definite fact that answers every directional question in one stroke. The electron has nothing of the kind. It has no single hidden axis that answers all directions. It can only ever hand you a definite answer to one direction, and that answer does not lock in the others. This is why, again and again, we're driven to say that the electron is not a little top. A top could never behave this way. Whatever the electron is, its spin lives in a state whose structure allows only one directional question to be answered sharply at a time. We can even ask what happens along a direction that is neither fully aligned with our first measurement, nor fully perpendicular to it, and the answer is elegant. If we first prepare a pure spin-up beam along the vertical, and then measure along a direction tilted at some angle between vertical and horizontal, we still get exactly two outcomes, up and down along that tilted direction, never a smear. But now the odds are no longer 50-50. The closer the new direction is to the original vertical, the more likely the electron gives the up answer along the new direction. The closer the new direction swings toward the perpendicular, the closer the odds slide toward 50-50. The probabilities shift smoothly with the angle, even though the outcomes themselves remain stubbornly discrete. So the discreteness of the outcomes and the continuity of the probabilities live side by side. You always get one of two answers, but how likely each answer is depends smoothly on how you tilt your question relative to how the electron was prepared. This blend of sharp outcomes and smooth odds is a fingerprint of quantum mechanics found nowhere in the classical world. Let me push that tilted angle picture a little further, because if you actually imagine slowly rotating the second magnet, watching the two spots shift their weights, you witness something that no classical object could ever do. Begin with the second magnet perfectly aligned with the first, both measuring the vertical direction. Send in the pure spin-up beam. Every atom sails to the up spot, and the down spot stays completely dark. There is no randomness at all here, because you are asking the electron the very same question it has already answered, and it gives the same answer every time with perfect certainty. Now begin turning the second magnet degree by degree away from vertical. At first, almost every atom still goes up, with only a rare few appearing in the down spot. As the magnet tilts further, the down spot brightens and the up spot dims, the two of them trading populations smoothly as the angle grows. At 90 degrees, at full perpendicularity, the two spots are exactly equal, a perfect 50-50 split. The electron now maximally uncertain about this new sideways question. Keep turning past 90 degrees and the balance tips the other way, and at a full 180 degrees, when the second magnet points exactly opposite to the first, every atom lands in what that magnet calls the down spot, with perfect certainty once again, because opposite down is simply up seen upside down. What you are watching as you turn that dial is the electron's certainty draining smoothly away and then refilling. A continuous flow of probability governed entirely by the angle between the question you asked before and the question you're asking now. And yet at every single setting of the dial, no matter how you tilt it, each individual atom still lands at one of exactly two spots. The graininess of the outcomes never softens, only the odds slide. This is the strangest marriage in all of physics. Outcomes that are rigidly, stubbornly discrete, riding on probabilities that are perfectly smooth and continuous. A spinning top would never do this. A top asked about a slightly tilted direction gives a slightly tilted answer. The electron refuses. It gives one of two sharp answers and adjusts only how often it chooses each. I want to linger on why physicists treasure spin as the purest example of this quantum strangeness, because it is not an accident that spin shows up in nearly every first lesson on the subject. Most quantum properties, like a particle's position or its momentum, can take on a whole continuum of values, an endless range of possibilities, and the mathematics that describes their incompatibility is correspondingly tangled. Spin is different. For an electron, the answer to any directional question is one of only two possibilities. This makes spin the simplest non-trivial quantum system that exists, the cleanest possible arena in which to watch incompatible questions interfere with one another. When physicists want to demonstrate that two measurements can genuinely refuse to have simultaneous answers, that asking one scrambles the other, they reach for spin, because there is nothing simpler that still shows the full weirdness. The endless continuum of positions hides the essential point behind mathematical thickets. The two little spots of a spin measurement lay it bare. In those two spots, and in the smooth way their brightness trades as you turn the magnet, you can see the entire logic of quantum incompatibility distilled to its absolute minimum. Now, let me gather everything this experiment has taught us, because it is a great deal. We learned that measuring spin along a direction gives discrete outcomes, not a continuous smear, and that for the spin 1/2 electron there are exactly two. We learned that these outcomes are not pre-existing labels being sorted, because a beam prepared definite along one direction splits again when measured along another. We learned that the measurement does not read a hidden arrow, but forces the particle to commit to one of the allowed answers for the direction we chose. We learned that spin components along different directions cannot all be definite at once, that they are non-commuting, that pinning one blurs the others. We learned that the total spin, the 1/2, is a fixed property, while the projection along a chosen axis is what the measurement extracts, one of two discrete values. And we learned that the label spin 1/2 is not a speed or a half turn, but a classification that dictates the two-outcome structure of every directional measurement. Every single one of these lessons drives a nail into the coffin of the spinning ball picture, and yet every single one confirms that spin is genuine, measurable, and governed by precise laws. This is the strange dual truth we keep arriving at from every direction. Spin is real. Spin is angular momentum. Spin can be measured with fantastic precision. And spin is nothing like a ball turning on an axis. It is a property of the electron's quantum state, a property whose behavior under measurement is quantized, probabilistic, and directionally incompatible with itself in ways that no rotating object could ever imitate. But there is still a question lurking underneath all of this, one that the stern Gerlach experiment hints at but does not fully answer. We keep saying that spin is angular momentum, and we keep saying that angular momentum is deeply connected to rotation. So if the electron is not a rotating object, in what sense is its spin connected to rotation at all? What is the hidden thread that ties this two-outcome, blend-forming, direction-scrambling property to the geometry of turning through space? The answer takes us into the most counterintuitive territory yet, a place where turning something all the way around does not bring it back to where it started, where an object must be turned twice around before it truly returns, and where the very meaning of orientation for a quantum state defies everything our hands and eyes have taught us. That is where we turn next, and it is there that the deepest secret of spin, the reason it deserves its name and yet refuses its picture, finally comes into view. We have been circling a single stubborn question, and now it is time to face it directly. We keep insisting that spin is angular momentum, and we keep insisting that angular momentum is bound up with rotation, yet we have also insisted over and over that the electron is not a rotating object. So there is a thread we have not yet followed to its end. If the electron is not a little sphere turning through space, then in what possible sense is its spin connected to rotation at all? What links this two-valued, blend-forming, direction-scrambling property to the plane geometry of turning? The answer is the deepest and strangest idea in this entire story, and it is the one that finally explains why spin deserves its name while forever refusing its picture. To reach it, we have to change what we think rotation even means when applied to a quantum thing. Here is the shift. In the everyday world, we think of rotation as something we do to an object. We grab a cup and turn it. We spin a globe. The object moves, its surface sweeps through space, and we watch the motion happen. But in physics, there is a deeper and more powerful way to think about rotation, one that does not require any object to move at all. We can ask a different question. If I rotate my entire point of view, my whole frame of reference, how does the mathematical description of a system change? Imagine you're describing where everything is, and then you turn your head, or turn the whole coordinate grid you're using, so that what you used to call up is now tilted. Nothing physical has moved. You have simply rotated the description. And the rules for how descriptions transform when you rotate your frame turn out to encode, precisely and completely, what angular momentum is. This is the secret hinge of the whole subject, so let me say it as plainly as I can. Angular momentum at the deepest level is not fundamentally about things going around. It is about how a system's description responds when space is rotated. A system carrying a lot of angular momentum has a description that changes in a rich, complicated way under rotation. A system carrying no angular momentum has a description that barely changes at all under rotation. The connection between rotation and angular momentum is so tight that physicists take it as the very definition. To have angular momentum is to transform in a specific way under rotations, and once you accept this definition, the mystery of spin begins to dissolve, because now the electron does not need to physically rotate to have angular momentum. It only needs to have an internal state that transforms in a particular way when space is rotated, and it does. That transformation behavior is its spin, turning without a thing that turns exactly as promised. But to really understand what kind of transformation behavior the electron spin has, we need to compare it to something familiar and then watch the comparison break in a way that will genuinely surprise you. So let us start with an ordinary arrow, a vector, the kind of thing that points in a direction in space. An arrow is the most natural picture of orientation we have. If you have an arrow pointing north and you rotate your frame by a certain angle, the arrow's description changes in a smooth, sensible way, tilting to match. And here is the crucial property of an ordinary arrow. If you rotate it all the way around through a full turn, a complete 360 degrees, it comes back exactly to where it started. Of course it does. A full turn brings anything back to its beginning. This is so obvious it barely seems worth stating. Turn a cup all the way around and it looks identical. Turn an arrow all the way around and it points the same way it did. A full rotation is a return to the starting point. This is one of the most basic facts our intuition knows. The electron's spin does not obey this rule. I want you to really absorb how shocking that sentence is, because it violates something so deep in us that we can hardly imagine an exception. The mathematical object that describes the electron's spin is not an ordinary arrow. It belongs to a different and stranger family of objects that physicists call spinors, and a spinor has a property that no arrow, no cup, no globe, no everyday object shares. When you rotate a spinor through a full turn, a complete 360 degrees, it does not come back to where it started. Instead, it comes back flipped, reversed in a subtle way, carrying an extra minus sign. To bring a spinor genuinely back to its original state, you have to rotate it twice around, through a full 720 degrees. Only after 2 complete turns does the electron's spin state truly return to itself. 1 turn is not enough. 1 turn leaves it inverted. Now, I have to be very careful here, because this is exactly the point where popular explanations go wrong and plant a false picture in people's minds. It is tempting to say that the electron must be physically rotated twice before it looks the same, as though the electron were a peculiar object with such strange geometry that a single turn does not restore its appearance. That is not the right way to understand it, and it can lead you badly astray. The electron is not a little shape that needs turning around twice to look right. The thing that transforms in this doubled way is not the electron's appearance in space. It is the electron's quantum state, and specifically a feature of that state called its phase. So let me build up what that means, because the phase is where the real action is, and it is far more beautiful than the cartoon of an object needing 2 spins. A quantum state, as we said long ago, is not a picture of a solid object. It is a mathematical description of possibilities and tendencies, and part of that description is a quantity called the phase. You can think of phase, loosely, as being like the position of a hand sweeping around a clock face, an angle that is part of the state's mathematical makeup but that does not, on its own, correspond to anything you can directly see. The phase is always there, quietly turning as the state evolves, but a curious feature of quantum mechanics is that the overall phase of a state taken all by itself, is invisible. You cannot measure it directly. Two states that differ only in their overall phase will give identical results for every measurement you could possibly perform. The phase hides, and this hiddenness is going to matter enormously at the moment. Now here is the connection to rotation. When you rotate the electron's spin state through a full turn, the state's phase advances by exactly half a clock's worth, by half a turn of that hidden clock, which is what produces the minus sign. A minus sign, in the language of these hidden clock angles, is exactly a half turn of the phase clock. So one full rotation of the electron in space corresponds to a half turn of its internal phase clock, leaving it with a flipped sign. Two full rotations of the electron in space correspond to a full turn of the internal phase clock, bringing it genuinely back to the start. That is the real content of the 720-degree property. It is not that the electron is a weirdly shaped object needing two spins to look right. It is that the electron's internal phase clock turns half as fast as the rotation of space itself, so that space must turn twice for the phase clock to turn once and return home. And now you can see why we had to spend time establishing that the overall phase is invisible. Because if a full rotation only flips the sign of the state, and the sign is part of the overall phase, and the overall phase cannot be directly measured, then the sign flip after one full turn is, on its own, undetectable. You could rotate an isolated electron all the way around, and by any measurement you make on that lone electron afterward, you would find no difference whatsoever. Its spin along any direction, its probabilities, everything you can measure would be identical to before. The minus sign is hiding inside the invisible phase. So in what sense is it real? In what sense does the doubled behavior mean anything at all if you can never catch it? The answer is one of the most elegant ideas in physics, and it is this. An overall phase is invisible, but a relative phase is not. If you take a single electron and rotate the whole thing, the sign flip is invisible because it applies to the entire state at once, and an overall phase cannot be seen. But if you could take an electron and split its quantum state into two paths, rotate only one of the paths through a full turn while leaving the other alone, and then bring the two paths back together, then the sign flip on one path becomes a difference between the two paths, and a difference in phase between two parts of a state that are then recombined is absolutely measurable. It shows up as interference, as a shift in the pattern you get when the two paths meet, in exactly the way that overlapping ripples on water can reinforce or cancel, depending on how their crests and troughs line up. This is not a thought experiment alone. Experiments of essentially this kind have been performed, using beams of particles that carry spin split into two paths, with one path subjected to a rotation and the other not. When the paths are recombined, physicists observe an interference pattern, and as the rotation on one path is increased, the pattern shifts, and the pattern only returns to its original form after that path has been rotated, not through one full turn, but through two. After a single full turn, the interference is maximally shifted, the crests lining up with the troughs, the telltale signature of that hidden minus sign made visible through comparison. The 720-degree behavior of the electron's spin state is therefore real and measurable, but only through interference, only by comparing one part of a state against another. The sign change becomes observable exactly when you set up a comparison and stays hidden whenever you do not. This is why we must never call it a disconnected novelty, a fun fact with no consequences. It is a genuine, tested feature of how spin states transform, revealed through the same interference physics that governs all of quantum mechanics. Let me offer an image that captures the spirit of this doubled rotation, while warning you it is only an aid and not the literal truth. Imagine a coffee cup resting on your flat, upturned palm. Now try to keep the cup upright while rotating it around, twisting your arm. As you turn the cup a full 360 degrees, you find your arm has become awkwardly twisted, your elbow jutting out uncomfortably, unable to continue smoothly. The cup has returned to its starting orientation, but your arm has not returned to its starting configuration. It is contorted. To untwist your arm, you cannot simply reverse. Instead, if you continue turning the cup in the same direction for another full 360 degrees, lifting it over your shoulder as you go, your arm miraculously unwinds and returns to its natural relaxed position. 2 full turns of the cup, and only 2, bring the whole system, cup and arm, together, back to its true starting state. The cup alone looked restored after 1 turn, but the full connection of the cup to its surroundings, through your arm, required 2. This is only an analogy, and the electron is not a cup and has no arm, but it captures something true, that there can be a kind of orientation which is not fully described by where an object points, a hidden connective bookkeeping that keeps track of the winding, and which requires 2 full turns rather than 1 to genuinely reset. The electron's spin state carries something like this hidden winding in its phase, and that is the honest heart behind the striking claim that the electron must be turned twice around. It is not the electron's appearance that needs 2 turns. It is the connective phase bookkeeping of its quantum state, made visible only when compared against a reference through interference. Now, having established that spin is fundamentally about how the electron state transforms under rotation in this doubled spinorial way, let me bring us back down from the abstract heights to something you can hold in your hand, because I do not want spin to feel like a purely mathematical curiosity. The rotation story is not just elegant geometry. It is directly responsible for physical effect you rely on every day, and the bridge from the abstract transformation behavior to the concrete effects runs through magnetism. Recall from much earlier that the electron produces a magnetic effect, that it behaves like a tiny magnet. We can now understand this more deeply. Because the electron carries angular momentum, and because the electron also carries electric charge, these 2 facts combine to give it a magnetic character. In the classical world, a loop of moving electric charge produces a magnetic field, which is how electromagnets work, coils of wire with current flowing around them. The electron's spin gives it a magnetic behavior that is analogous in its effect. A magnetic moment, a built-in tendency to align with or against magnetic fields, and to feel forces in uneven fields. This is precisely the magnetic character that let the stern Gerlach magnet push the atoms up or down. The spin angular momentum and the magnetic moment are tied together, 2 faces of the same underlying property. But notice what we can now say that we could not say before. This magnetic moment does not require the electron to be a spinning charged ball. We spent a great deal of effort demolishing that ball on the grounds we laid out earlier. The magnetic moment instead arises from the electron's intrinsic spin, which is a property of its quantum state and its transformation behavior under rotation, not a consequence of charge physically circulating around an axis. And this is why the magnetism came out with that puzzling factor of roughly 2 that the classical ball could never explain. When the correct theory of the electron is written down, one that properly weds quantum mechanics to the requirements of relativity, that factor of 2 emerges naturally, without any spinning ball, straight from the mathematics of how a spin 1/2 state must behave. The very number that broke the classical picture is delivered effortlessly by the quantum one. This is one of the great triumphs that convinced physicists they were on the right track. The theory did not merely accommodate spin, it predicted the electron's magnetism correctly, factor of 2 and all. And because spin carries genuine angular momentum, and also this magnetic moment, it can do real physical work in the world. Let me give you the concrete consequence I promised, the one you have almost certainly encountered without knowing spin was behind it. When a patient slides into a medical scanner that produces detailed images of the soft tissues inside the body, the images are built on the spin of atomic nuclei, chiefly the nuclei of hydrogen atoms in the water and fat that fill our bodies. Each of those nuclei carries spin and, with it, a magnetic moment. When placed inside the scanner's powerful magnetic field, these nuclear spins have a tendency to align with the field, much as the electrons did in our earlier story. The machine then sends in carefully tuned pulses of radio waves, and here is where the magic of spin's angular momentum shows itself. The radio waves carry energy and angular momentum, and they can flip the nuclear spins, tipping them away from their alignment. When the pulse stops, the spins gradually return toward alignment, and as they do, they release energy that the machine detects. The rate at which the spins return, and the signals they give off as they do, depend delicately on the chemical surroundings of each nucleus, on whether it sits in water or fat, in healthy tissue or diseased tissue. By reading these spin signals from throughout the body and reconstructing where they came from, the machine builds a detailed picture of the interior without a single cut. This entire technology, which has saved countless lives and revealed the workings of the living brain, rests on the fact that atomic nuclei carry intrinsic spin, that this spin comes with a magnetic moment, and that angular momentum can be handed back and forth between radio waves and spins. If spin were a fiction, if nothing real were there to be flipped and to relax, none of it would work. Every image is a testament to the reality of spin's angular momentum. And notice that this same principle, that spin can transfer angular momentum, is the very thread running through the demonstrations we met at the very beginning. The twisting light and the turning cylinder. In every one of them, spin angular momentum flows into or out of ordinary mechanical rotation. The books balance. Angular momentum is conserved. What began inside a quantum state as an abstract transformation property ends up as the visible turning of a real object, or as the detectable signal in a medical scanner, or as the force that split a beam of atoms into 2. The abstract and the concrete are the same thing, seen from different sides. Let me now tie the rotation story and the magnetism story together into a single coherent picture, because they are not 2 separate facts, but 2 expressions of one underlying truth. Spin is intrinsic angular momentum. Angular momentum is defined by how a state transforms under rotation. The electron spin state transforms in the doubled spinorial way, which is what marks it as a spin 1/2 object. Because the electron also carries charge, this angular momentum is accompanied by a magnetic moment, whose precise size the deep quantum theory delivers as an automatic consequence rather than an assumption we must feed in by hand. And because the spin carries real angular momentum and real magnetism, it can be measured, manipulated and transferred, showing up in everything from the 2 spots on a stern Gerlach screen to the images of a medical scanner. Every thread we have pulled leads back to the same knot. Spin is a genuine physical property rooted in the geometry of rotation, carried by the quantum state rather than by any moving surface. I want to guard one more time against a misreading that the vividness of the rotation story could accidentally encourage, because it is so easy to take that story too literally. When we say spin is connected to rotation, we do not mean that the electron is secretly spinning after all, that we have quietly smuggled the ball back in through the language of transformations. We have not. The connection to rotation is a connection to how the state responds when space is rotated, which is a statement about the structure of the state, not about any physical whirling of a body. The electron sits at its point, sizeless, surfaceless, and yet its state carries this rotational fingerprint, this spinorial transformation law, that entitles it to genuine angular momentum. Rotation is woven into the definition of spin, but no rotating object is required to supply it. That is the resolution of the paradox we opened with, seen now from the highest vantage point we've reached. Turning without a thing that turns is not a contradiction once you understand that angular momentum was never really about a thing going around. It was always, at the deepest level, about how descriptions transform under the turning of space itself. There is a further beauty here that I do not want to pass by. The existence of these 2 families of behavior under rotation, the ordinary arrow-like objects that return after 1 turn and the spinorial objects that require 2, is not something physicists invented to describe spin. It is a fact about the geometry of rotations in 3-dimensional space, a mathematical structure that exists whether or not any electrons are around to embody it. When you carefully study the ways that rotations in our 3-dimensional world can combine and compose, you find that they naturally allow for these 2 kinds of objects, the ones that come back after 1 full turn, and the ones that come back only after 2. The single-turn objects are the vectors and tensors we use to describe fields and stresses and ordinary orientations. The double-turn objects are the spinors. Nature, it turns out, uses both. The particles that build matter, the electrons and their kin, are spinorial double-turn objects. And this is not an arbitrary choice. As we will see, it is bound up with the deepest reasons that matter is stable, and that identical particles keep their distance from one another. The strange double-turn geometry of spin is not a footnote. It is written into the foundations of why the physical world holds together at all. It is worth pausing on just how deeply this 2-family structure is rooted, because it is not a quirk of electrons or a feature someone bolted onto the theory. It is a consequence of the shape of rotations themselves. Think about all the ways you can rotate an object in 3-dimensional space, every possible tilt and turn and combination of turns. These rotations form a kind of landscape, a space of their own, and that landscape has a subtle feature. It is, in a precise mathematical sense, doubly connected. Loosely, this means there are 2 distinct classes of rotational paths that return you to where you started, and no smooth way to deform one class into the other. A path that turns once around belongs to a different class than a path that turns twice around, and you cannot slide the first into the second without cutting it. This is a fact about the geometry of turning, true whether or not a single particle exists anywhere in the universe. And because rotations have exactly this double character, any object that responds to rotations must respond in one of exactly 2 ways. Either it ignores the distinction between the 2 classes of path, returning to itself after a single turn like an ordinary arrow, or it registers the distinction flipping its sign after one turn and only truly returning after two, like a spinor. There is no third option, and there is no way to avoid the choice. Nature did not decide to make electrons spinorial as a design flourish. The geometry of space left only two doors, and the particles of matter walk through the second one. When you hold this in your mind, the 720-degree behavior of the electron stops feeling like an isolated marvel and starts feeling like an inevitability, a direct imprint of the structure of rotation stamped onto the deepest constituents of the world. So let us take stock of where the journey has carried us. We asked how spin could be angular momentum if the electron does not rotate, and we found the answer in a redefinition of what angular momentum means. Not the going around of an object, but the transformation of a state under rotation. We discovered that the electron's spin state is a spinor, a strange object that requires two full turns rather than one to return to itself, and we were careful to locate this strangeness in the state's hidden phase rather than in any physical appearance, and to explain that the sign flip after one turn is invisible alone but real and measurable through interference. We connected this rotational nature to the electron's magnetic moment, saw the correct theory deliver the puzzling factor of 2 that the classical ball could never produce, and followed spin's angular momentum out into the concrete world of medical imaging and twisting objects, where it does genuine physical work. Through all of it, the same lesson held. The angular momentum is genuine and rooted in the geometry of rotation, and yet no ball is turning anywhere to supply it. But there is a further reach to spin, one that goes beyond any single electron and touches the very architecture of matter. For it turns out that whether a particle's spin state is of the single turn kind, or the double turn kind, whether it is a spinor or an ordinary object, determines something astonishing about how such particles behave when there are many of them together. It determines whether they are willing to crowd into the same state or whether they fiercely refuse to. It determines why the electrons in an atom stack themselves into orderly layers rather than all collapsing into one. It determines why you do not fall through your chair, why matter takes up space, why the periodic table has the shape it does, why chemistry exists, why you exist. The double-turn geometry we have just uncovered is the hidden reason that solid matter is solid, and that is where we turn next, to see how this abstract property of rotation becomes the very foundation of the material world. We ended on an audacious promise that the strange double-turn geometry of spin, this abstract fingerprint of how a quantum state responds to rotation, is the hidden reason that solid matter is solid, that you do not sink through your chair, that the periodic table has its shape, that chemistry and therefore life exists at all. That is an enormous claim to hang on something as ghostly as a spinner's transformation law. So let us earn it, step by careful step, and watch an abstract property of rotation become the very scaffolding of the material world. The bridge from spin to the structure of matter runs through a single profound fact, one of the deepest in all of physics. The amount of spin a particle carries determines how it behaves in the company of identical particles. This is the connection between spin and what physicists call statistics, the rules that govern crowds of indistinguishable particles, and it sorts every particle in the universe into two great families, divided precisely by their spin. On one side stand the particles whose spin comes in half integer amounts, spin 1/2, like the electron, or spin 3/2, and so on. These are the particles that transform in the double-turn spinorial way we uncovered, the ones that pick up a minus sign after a single full rotation. Physicists call them fermions, On the other side stand the particles whose spin comes in whole integer amounts: spin 0, spin 1, spin 2. These transform in the ordinary single-turn way, returning to themselves after one full rotation, like arrows. Physicists call them bosons. Every particle you've ever heard of falls into one camp or the other, and the dividing line is exactly the nature of its spin. Half-integer spin makes a fermion. Whole integer spin makes a boson. This is not a minor taxonomic detail. It is one of the great organizing principles of nature, and here is why the division matters so enormously. Fermions and bosons behave in opposite ways when you try to put several identical ones into the same quantum state. Bosons are gregarious. Identical bosons are perfectly happy to pile into the same state together, as many as you like, all sharing the same condition. This sociability of bosons underlies phenomena like the laser, where enormous numbers of particles of light march in lockstep in a single shared state, producing that pure, coherent beam. Fermions are the exact opposite. Identical fermions absolutely refuse to occupy the same quantum state. No two of them will ever be found in precisely the same condition. This refusal has a name that you may have heard before, the Pauli exclusion principle. And it is this stubborn refusal, this deep unwillingness of identical fermions to share a state, that builds the material world. Now, I must immediately guard against the wrong picture, because the exclusion principle is often described in ways that quietly smuggle back in the spinning ball we worked so hard to destroy. It is tempting to imagine that the electrons refuse to occupy the same state, because they are physically spinning objects that would somehow collide, that their little surfaces would grind against one another. That exclusion is a kind of crowding, a matter of particles bumping and jostling for room. This is entirely wrong. The exclusion principle has nothing to do with particles physically spinning into one another or pushing each other away through contact. There is no contact. There is no grinding of surfaces. The electrons need not be near each other at all for the principle to operate. Exclusion is not a force in the ordinary sense, not a shove that one electron gives another. It is a far deeper structural fact about how the combined quantum state of identical fermions is put together, and it is rooted directly in that spinorial, double-turn character we studied. Let me try to convey where the exclusion principle really comes from, because it is one of the most beautiful arguments in physics, and it ties directly back to everything we have built. When you have two identical particles, the combined state describing both of them has to account for the fact that the particles are genuinely indistinguishable. You cannot label one electron as electron A and the other as electron B in any way that nature respects, because all electrons are perfectly, absolutely identical. There is no scratch, no tag, no serial number that distinguishes one from another. So the combined description must behave sensibly when you imagine swapping the two particles, exchanging their roles. Nature is indifferent to which is which, so swapping them cannot change anything you could measure. But here is the subtle and crucial point. Although swapping two identical particles cannot change anything measurable, it can do to the combined state exactly the kind of thing we saw a full rotation do to a single spinor. It can leave the state unchanged, or it can flip its sign. And which of these happens is dictated by the spin of the particles. For bosons, whole integer spin particles, swapping two of them leaves the combined state exactly as it was, unchanged sign and all. For fermions, half-integer spin particles, swapping two of them flips the sign of the combined state, introducing that same minus sign we met when rotating a spinor once around. This deep link, that the sign flip under exchange follows from the spin, is one of the most remarkable results in physics. A theorem connecting the spin of a particle to its statistical behavior, and it is precisely the connection between the double-turn geometry of spinors and the refusal of matter to overlap. Now watch what that sign flip does. Suppose you try to put two identical fermions into exactly the same quantum state, the same condition in every respect. Then the two particles are not merely identical, they are in identical situations, and swapping them changes literally nothing because there is nothing to change. But we just said that swapping two fermions must flip the sign of the combined state. So the combined state must equal both itself and its own negative at the same time. The only quantity that equals its own negative is zero, and a state equal to zero is no state at all. It describes nothing. It cannot exist. Therefore, two identical fermions simply cannot be in the same quantum state. The mathematics forbids it, not through any force or collision, but through the pure structural requirement that the state flip sign under exchange while representing a genuine possibility. The Pauli exclusion principle falls out of the spinorial nature of fermions like a theorem, inevitable and exact. This is what it means when we say the double-turn geometry of spin is written into the foundations of matter. The very same minus sign that hid in the electron's phase after one rotation reappears here in the exchange of two electrons, and it is this minus sign that keeps electrons apart. Now let us cash out this principle in the structure of an atom and watch chemistry itself emerge. An atom has a small, dense nucleus, and around it the electrons arrange themselves into quantum states, often pictured loosely as shells or layers, though we should be careful with that word. Each of these available states has a definite energy and a definite spatial character, its own way of wrapping the electron's wave around the nucleus. Now, because electrons are fermions, no two of them can share the same quantum state. So as you add electrons to an atom, they cannot all collapse down into the single lowest energy state, the way a crowd of sociable bosons would. Instead, each electron must find a distinct state of its own. The lowest state fills, and then the next electron is forced into a higher one, and the next into a higher one still, stacking upward through the available states because exclusion bars them from doubling up. But there is a wrinkle that spin itself provides, and it is a lovely one. Because each spatial state can pair with two spin conditions, spin up and spin down along some direction, two electrons can occupy what is otherwise the same spatial state, provided their spins differ. They are then not in truly identical quantum states, because their spins distinguish them, and so exclusion is satisfied. This is why electrons fill the atomic states in pairs, two to each spatial arrangement, one spin up and one spin down, and then no more. The spin provides exactly a doubling of the available slots, and this doubling is stamped all over the structure of matter. Follow this through, and the periodic table of the elements unfolds before you. The pattern by which electrons fill the available states, two by two, then moving to the next level, then the next, determines how many electrons sit in the outermost region of each atom. And the number of outer electrons determines how an atom bonds with others, how it shares and trades electrons, which is to say it determines the atom's entire chemical personality. The reason the elements fall into the columns and rows they do, the reason some elements are inert and others fiercely reactive, the reason carbon can form the vast scaffolding of life while helium sits aloof and unreacting, all of it traces back to how electrons stack into states under the discipline of exclusion, with spin providing the pairing. Chemistry, the whole magnificent edifice of it, is the shadow that the Pauli exclusion principle casts across the atoms. And exclusion, we have seen, is nothing but the spinorial double-turn geometry of the electron, expressed in the exchange of identical particles. And now the promise about your chair. Why does matter take up space? Why can you not push your hand through the table, given that atoms are, as we noted long ago, almost entirely empty? A tiny nucleus and a sparse cloud of electrons with vast emptiness between. If atoms are mostly void, why is solid matter solid at all? The answer is exclusion. When you press two objects together, you're trying to force their electrons into overlapping states, into the same conditions in the same region. But the electrons are fermions, and they refuse. They cannot be squeezed into shared states, and this refusal expresses itself as a genuine resistance, a stiffness, a pressure that pushes back against the compression. This is not the electrical repulsion of like charges, though that plays its own role. It is a distinct and deeper effect arising purely from the exclusion principle, sometimes called degeneracy pressure. It is the reason matter is rigid, the reason floors hold you up, the reason a chair is a chair and not a region you drift through. When you sit down, the exclusion principle is what catches you. The abstract minus sign of the spinor, riding through the exchange of electrons, becomes the solidity of the world under you. This same exclusion pressure holds up entire dying stars. When a star like our Sun exhausts its fuel and collapses, it is halted, not by any fire or fuel, but by the refusal of its electrons to be crushed into the same states. The resulting object, a white dwarf, is held rigid against the crushing weight of its own gravity by electron exclusion pressure alone. Push harder in a more massive star, and even the electrons can be overwhelmed, but then the neutrons, which are also fermions, take up the refusal, and their exclusion pressure holds up a neutron star, an object with the mass of a sun packed into the width of a city. The stability of these stellar corpses, scattered across the galaxy, is a monument to the exclusion principle written on a cosmic scale. From the chair beneath you to the dead stars in the sky, the double-turn geometry of spin is holding matter apart. Before we return inside the atom, I want to give the sociable side of this story its due, because so far the bosons have appeared only as a foil, the easygoing opposite of the standoffish fermions. But their willingness to share a state is not merely the absence of a rule. It is a positive power in its own right, and it produces some of the most striking phenomena in nature. Because identical bosons are perfectly happy to pile into the same quantum state together, you can gather an enormous number of them all doing precisely the same thing, all marching in perfect step. This is exactly what happens inside a laser. A laser is, at its heart, a vast throng of particles of light, all crowded into a single shared quantum state, all with the same direction, the same colour, the same phase of their waves. That is why laser light is so pure and so tightly focused, so unlike the scattered glow of an ordinary bulb whose particles of light go every which way in every colour. The coherence of a laser, the very property that lets it cut steel or carry information down a glass fibre or read the pits on a disk, is a direct gift of bosonic sociability. If particles of light were fermions, refusing to share states, the laser could not exist. So the same spin distinction that makes matter rigid and structured makes light capable of marching in unison. Fermions build the walls, bosons carry the messages. The world needs both, and both consequences flow from nothing more than whether a particle's spin is a whole number or a half. Now let me spin into a consequence that reaches beyond the structure of matter into the very transformations that particles undergo, because this is where the conservation of spin shows its teeth. Angular momentum, we have said again and again, is conserved. The total amount of turning in a closed system cannot change, and spin, being genuine angular momentum, must be included in that accounting even when particles are created and destroyed. Consider what happens when an unstable particle decays, breaking apart into two or more lighter particles. This is not a rare event. Countless particles throughout the universe are unstable, living for a fleeting moment before transforming into others, and whenever such a transformation occurs, the books of angular momentum must still balance. The total spin of everything that comes out combined with any orbital angular momentum carried by their flying apart has to add up to exactly the spin of the particle that went in. This is not a loose guideline. It is an ironclad law that rules out entire categories of decay before they can even happen. A particle of a given spin simply cannot decay into a collection of particles whose spins and orbital motions have no way of summing to the original value. Nature forbids it, and no such decay is ever observed. When physicists puzzle over which transformations a particle is allowed to undergo, one of the very first filters they apply is this: can the angular momentum possibly balance? If the answer is no, the decay is struck from the list of possibilities no matter what else might permit it. And this filtering has been confirmed in countless experiments in the great particle accelerators where unstable particles are made and watched as they fall apart. The patterns of what decays into what and in which directions the fragments fly all obey the conservation of angular momentum with spin fully included. Here is spin doing something far removed from atoms and chairs and stars. It is governing the fundamental transformations of matter itself, dictating which particles can become which, and it does this with no little object wheeling around inside any of the particles involved. The angular momentum belongs to the quantum states, and the states must balance their ledgers whenever one particle becomes several. There is one more arena where spin quietly runs the show, and it sits right at the center of every atom, the nucleus. We spoke of the proton assembling its spin from quarks and gluons and internal motion, but step up one level and ask what happens when many protons and neutrons gather together into a nucleus. Each of those protons and neutrons is a fermion carrying spin 1/2, and inside the nucleus they arrange themselves according to their own version of the exclusion principle, filling nuclear states 2 by 2 just as electrons fill atomic states, their spins pairing off. When the pairing is complete and every spin is matched by an opposite, the spins largely cancel. But when there is an odd one left over, or when the internal motions do not fully cancel, the nucleus as a whole is left with a net spin of its own, a total angular momentum belonging to the entire cluster of particles. Different kinds of nuclei end up with different net spins, some 0, some 1/2, some larger, depending on how their protons and neutrons have arranged and paired, and that net nuclear spin is not a mere curiosity of bookkeeping. It is the very thing that makes the medical scanner possible, the property that the powerful magnet grips and the radio waves flip. Only nuclei that possess a net spin can participate, which is precisely why the hydrogen nuclei scattered through the water and fat of your body are the workhorses of the image, each one a lone proton carrying its unpaired spin 1/2 like a tiny compass needle waiting to be turned. The whole technology rests on this ladder of spin, from the quarks that give the proton its spin, to the proton that carries that spin into the nucleus, to the nucleus whose net spin the scanner reads. It is spin all the way up, each level assembling into the next, until the abstract angular momentum of quantum states becomes a detailed photograph of the living brain. And nowhere in that entire ladder is there a single spinning ball. There is only angular momentum layered and combined and conserved, belonging at every rung to the quantum states of the particles rather than to any rotating surface. Let me now return inside the atom for one more refinement, because I do not want to leave you thinking spin and orbital motion are entirely separate accounts that never speak to each other. We drew a sharp line earlier between intrinsic spin, the built-in angular momentum of the particle itself, and orbital angular momentum, the angular momentum an electron has by virtue of how its wave wraps around the nucleus. These are genuinely different things, and it is important to keep them distinct. But within an atom, they are not entirely indifferent to one another. They can couple, they can talk, in an effect called spin-orbit coupling. Here is the intuition, handled with care. An electron moving through the electric field of the nucleus experiences, from its own point of view, effects that link its spin to its orbital motion. The electron's spin carries a magnetic moment, as we have discussed, and its orbital motion around the nucleus is associated with its own magnetic effect, and these two can interact so that the energy of the electron depends slightly on how its spin is oriented relative to its orbital motion. The spin and the orbital angular momentum become coupled, their orientations no longer wholly independent. This coupling is usually a small effect, a fine adjustment rather than a gross feature, but it is real and measurable. It splits atomic energy levels into closely spaced sublevels, producing subtle structure in the light that atoms emit and absorb, a fine structure that spectroscopists can read like fingerprints. Spin-orbit coupling is the reason certain spectral lines that would otherwise be single appear, on close inspection, as delicate doublets. It is one more place where intrinsic spin, though never a rotating ball, leaves an unmistakable mark on the physical world, this time by entangling itself with the genuine spatial motion of the electron around its nucleus. Yet even here, we keep the atomic details subordinate. The headline is that intrinsic spin and orbital angular momentum are distinct in origin, spin belonging to the particle's state and orbital belonging to motion through space, while nature permits them to couple in ways that fine-tune the structure of every atom. Now I want to widen the lens considerably, because so far we've spoken almost entirely of the electron, and I promised long ago not to let this become a story about electrons alone. Spin is carried by a great variety of particles, and when we look at composite particles built out of smaller pieces, we encounter a fascinating twist on everything we have said. Consider the proton, one of the building blocks of every atomic nucleus. The proton has spin 1/2, exactly like the electron, and in that sense it too is a fermion, subject to exclusion, transforming in the spinorial double-turn way. But the proton is not a fundamental particle in the way the electron is. The proton is composite. It is built from smaller particles, quarks, bound together by the particles that carry the strong force, called gluons. And here is the twist. The spin of the proton, that neat 1/2, is not simply the spin of a single object turning. It is assembled from several internal contributions. There are the spins of the quarks inside, which can point in various directions and add up in various ways. There is angular momentum carried by the gluons that bind the quarks, and there is orbital angular momentum from the internal motion of the quarks and gluons as they swirl within the proton. All of these internal pieces, the quark spins, the gluon angular momentum, and the internal orbital motion, combine together to produce the proton's total spin of 1/2. Untangling exactly how much each contribution provides has been one of the great experimental challenges of modern physics, a puzzle that surprised researchers when they discovered that the quark spins alone account for only a portion of the total, with the rest hidden in gluons and orbital motion. The proton's spin is a rich internal accounting, a sum for the angular momenta of its constituents. I dwell on this because it draws an important distinction that keeps our whole story honest. When we say the electron's spin does not come from anything rotating inside it, we mean it precisely because the electron appears to be truly fundamental, a point with no internal parts, so there is nothing inside it to move or to carry orbital angular momentum. Its spin is genuinely intrinsic, irreducible, not built from pieces. But the proton is different. Some of the proton's spin genuinely does come from internal motion, from quarks orbiting within it, from the swirling of its constituents. So we must be careful not to overgeneralize the slogan that nothing is spinning. For a composite particle, there is real internal structure and real internal angular momentum contributing to the whole. The lesson is not that internal motion never contributes to spin anywhere. The lesson is that for a truly fundamental particle like the electron, there are no internal parts to supply the angular momentum, and yet the spin is still there, still real, still 1/2, still spinorial. Intrinsic spin, in the strict sense, is the angular momentum a particle has even when it has no parts and no internal motion at all. The proton borrows some of its spin from its innards. The electron has no innards to borrow from, and its spin is pure and irreducible. Let me bring in one more kind of particle, because it completes the picture and illustrates that spin wears different faces on different particles. The photon, the particle of light. The photon carries spin, but it is a spin 1 particle, a boson, an integer spin particle that transforms in the ordinary singleton way rather than the doubled spinorial way. And the photon behaves nothing like a spinning bead. In fact, the photon has no rest mass and can never be brought to a stop, always moving at the speed of light, and its spin manifests in a form you may know by another name, polarization. When we describe light as polarized, as vibrating in a particular orientation, we are describing the manifestation of the photon's spin, the way its associated field is oriented as the light travels. Polarized sunglasses, the shimmer of light off water, the way certain screens dim when you tilt your head, all of these involve the polarization of light, which is the outward face of the photon's spin. I mention polarization only to clarify the relationship between spin and the underlying field, and I will not expand it into a full account, because that is a story for another time. The point I want you to carry is this: spin is not one single kind of thing wearing one costume. For the electron, it appears as a two-valued spinorial property that governs exclusion and builds matter. For the photon, it appears as polarization, a property of an oscillating field that always races along at light speed. The photon carries genuine spin angular momentum, which is why, as we noted at the very beginning, a beam of light can physically twist a suspended object, transferring its angular momentum into visible rotation. But the photon is emphatically not a little rotating pellet of light. Its spin is a property of the electromagnetic field itself, of how that field is oriented and how it transforms under rotation, just as the electron's spin is a property of its quantum state. In every case, spin is about how something transforms under rotation, and in no case is it a tiny ball turning on an axle. The unity beneath the diversity is the transformation law, not any spinning body. Now let me pull all of this up to the highest and most important level. because I want to dispel any last suspicion that spin is some optional extra, a curious property that particles happen to have, a label bolted on after the real physics was already written. Nothing could be further from the truth. Spin is not an afterthought. It emerges necessarily and inevitably when you combine quantum mechanics with the symmetry of space and the requirements of relativity. When physicists tried to write down a description of the electron that respected both the rules of quantum mechanics and the demand of relativity that space and time be treated on the proper footing, they found that spin fell out of the equations on its own, unbidden and unavoidable. They did not put it in by hand. It appeared, demanded by the very structure of the theory, the spinorial nature and the factor of 2 in the magnetism arriving together as a package, forced by the marriage of the quantum and the relativistic. This is a stunning thing to sit with. Spin is what you get when you ask how quantum states must transform under the symmetries of space-time. It is a direct consequence of the fact that we live in a world with the particular rotational and relativistic structure that we do. The two families, the single-turn objects and the double-turn spinors, are not options someone chose. They are the possibilities that the geometry of rotations in our universe allows, and nature populates both. Matter is built from the double-turn kind because that is what fermions are, and fermions are what can build stable, structured, space-filling matter through exclusion. Force and light are carried in part by the single-turn kind. The very fact that the universe contains both stable matter and the forces that act on it is bound up with the existence of both kinds of spin. Remove spin from physics and you do not merely lose a property, you lose the possibility of the periodic table, of chemistry, of solid matter, of the dense stellar remnants that resist their own collapse, of the structured world entirely. Spin is not decoration on the theory, it is load-bearing. At the same time, I want to be honest about the boundary between what physics can do and what it cannot, because intellectual honesty demands it. Physics can predict the behavior of spin with staggering precision. The magnetic moment of the electron, that quantity tied to its spin, has been calculated and measured in agreement to more decimal places than almost any other prediction in all of science. One of the most precisely confirmed results humanity has ever achieved. We can predict how spins will behave in magnetic fields, how they will split beams, how they will fill atoms, how they will hold up stars. The theory of spin is not vague or speculative. It is among the most tested and triumphant achievements of the human mind. What physics does not do, and does not pretend to do, is answer the deeper philosophical question of why the universe has this property at all, why reality is built so that quantum states carry these rotational fingerprints. That is a question of a different kind, and we should not confuse our extraordinary ability to predict spin's behavior with a claim to have explained why existence is furnished this way. The prediction is certain, the ultimate why remains open, as such ultimate whys tend to. And I want to close the door firmly on the tempting errors that lie on either side of the truth. On one side is the error of the spinning ball, the belief that the particle really is a tiny rotating sphere. We've destroyed that thoroughly. The surface would outrun light, the magnetism would come out wrong, and the particle shows no size or structure to rotate. On the other side is the opposite error, the overcorrection into which careless explanations fall. The claim that nothing is spinning in a sense that denies the reality of the angular momentum altogether. That spin is merely a name, a mathematical trick, a bookkeeping convenience with no physical substance. That error is just as wrong as the first, Spin is real angular momentum, with a whole catalogue of demonstrable effects behind it, from the beams it splits to the images it builds to the matter it assembles. To call it a mere trick is to ignore everything it verifiably does in the world. The truth lives precisely between these two errors, and the title we began with points exactly at that truth. When we ask why nothing is actually spinning, the answer is not that spin is unreal. The answer is that intrinsic spin is not ordinary mechanical rotation. There is no material object turning through space, no ball, no surface, no axis with mass sweeping around it, and yet the angular momentum is entirely real, because angular momentum was never fundamentally about a body going around. It was always, at the deepest level, about how a state transforms under the rotation of space. The electron possesses that transformation property in full. It carries genuine angular momentum, produces genuine magnetism, obeys genuine conservation laws, and builds the genuine solid world, all without any part of it needing to rotate like a top. That is what nothing is actually spinning means. Not that spin is absent, that the classical mechanical picture behind it is what is absent, replaced by something deeper. And so we arrive at the resolution of everything we have traced. Spin 1/2 never meant the electron was turning at half of some speed, or rotated halfway around, or half participating in a rotation. It meant that the electron's quantum state belongs to the double-turn spinorial family, giving two outcomes along any measured direction, and requiring two full rotations of space to return its phase to itself. The word spin was never a mistake, because the quantity is angular momentum in every way that can be tested. The spinning ball was the mistake, and only the ball. What remains once the ball is cleared away is one of the purest and most astonishing lessons in all of physics, that nature can keep a familiar physical quantity entirely intact, its conservation, its magnetism, its capacity to turn real objects and build real matter, while completely replacing the classical picture underneath it. The angular momentum does not belong to a spinning body. It belongs to the quantum state itself, woven into the way particles exist, transform under rotation, interact with fields, and assemble into everything you can see and touch and are. Nothing needs to spin like a ball, because the turning was never in a ball. It was in the deep structure of reality all along,